Welcome everyone to the fifth week of this course. So, as usual, we will recall some of the important results which have been discussed in the classroom, and then we'll solve some exercises uh, which are given as assignments to you. Okay, so how did we start it? Let me show this week 5 lecture notes. We'll discuss something from here. No need to write once more, and then we'll go forward. So, we have defined Riemann integral of f in real numbers when f is continuous function on intervals. This is how we define Riemann integral, which is the limit of these Riemann sums. Okay, so a similar definition has been given for complex valued functions uh, over not actually interval here, or image of intervals, means over the curves. Okay, when f is continuous on some curve gamma, then we define similar Riemann sum, but now these are complex numbers. And still, when partition goes to 0, this limit exists. This is the proposition here, this proposition, and this limit is called integral of f over gamma. And after this proposition, some results about integrals, how this integral behaves. For example, if gamma prime is another representation of curve gamma, I mean reparameterization of gamma, then gamma and gamma prime over whatever you take integral is not going to change. Okay, so this is first property of integral, and the second property is that if we take negative of the first curve here, minus gamma is defined to be reverse of the gamma. Okay, here we actually can see it. Okay, I don't want to disturb this PDF, so I hope you have already gone through these properties. And the next property is that if we have concatenation of two curves, gamma 1 plus gamma 2, then integral over gamma 1 plus gamma 2 is sum of the integrals over individual curves. Okay, this is third property, which is given as exercise, but this is trivial exercise. Just Riemann sum will be broken into two sums, and that then we take limit over different two different sums, we get individual integrals. And change of variable is actually the proof is given here. Gamma of f, sorry, integral of f over gamma is also equal to integral over ab, interval ab of this function f of gamma t into gamma prime t. Okay, so uh, the this is good thing that here on the left side it is integral over gamma curve, but on the right side it is integral over interval, right? So after this there's nothing much. uh, so this six properties about linearity of integral is which you already know from. This is also similar. The proof will be given for six sums. So it is given as exercise, but I'm telling you this exercise is not that difficult. Riemann sum, right? Riemann sum for the left, and it can be broken into two parts using linearity, because some uh, yeah. So take limit both sides when partition is going to 0, partition length is going to 0, then you will get this. And fifth property is that when f is taking maximum value, maximum mod m, then whole integral. So there is a little mistake here in the fifth. What is mistake? Can you tell me? . So in the fifth, there is a little mistake. Fifth probability. Do you see what is mistake here? Just a silly mistake, I would say. Maybe professor has told a correct thing, but while writing he missed it. So let me tell you, because nobody is responding right now. On the left side here, we have complex number. So this integral will be complex number. On the right, we have a real number. But if it is not real, this integral is, let's say, not real. How will you compare with the other? So the mistake is here it was modulus. Okay, modulus of this integral is less than equal to m into length of gamma. Okay, so after this, we have first fundamental theorem and second fundamental theorem. First fundamental theorem says when omega is an open connected subset of a C, it is a domain, and f is continuous function on this given domain, and such that it has an antiderivative. Antiderivative means this capital F type function, which are actually holomorphic, and when you take their derivative, you get f. This is definition of antiderivative. When small f has antiderivative, then um, this integral actually depends on the curve gamma this way, f of capital F of z1 minus f of z0, where this z1 is initial point, z0 is terminal point. Sorry, z0 is initial point and z1 is terminal point. Okay, so the proof is, I think, uh, not that obvious, but proof is given in, it takes, yeah, but here it is, in this case it is clear. We are just using the this part, this exercise. Okay, so this is the important step which we follow and we get the integral value, right? Now going to second fundamental theorem. The second fundamental theorem is some sense good. That gives us actually antiderivative of f. F is any continuous. Oh, sorry. Okay, so when we have omega a non-empty open connected subset, and f is a continuous function on omega, such that over closed curves. Why I'm saying closed curves, not closed polygonal path, because in the next theorem in the here is also, next theorem is given as this gamma can be this gamma integral of f. This is approximated with the integral of f over some polygonal path. Polygon.
So like in the first fundamental theorem, like can you give some like more insight, like higher level insight as to why that should be true, even if the number is complex, right? In when we do the Riemann integral for real numbers, it is like fairly obvious, but
Mm-hmm.
but here we have also the additional condition that it is a holomorphic also. So that alone is enough for like can you give some other higher level intuition onto why this should be true?
Actually, I don't know what do you mean by higher level, but the proof is obvious here. If you see here in
Yeah,
this
proof is
exercise,
like clear. Proof is clear, of course, but like in some, is there any other way of thinking about it, or like?
I think that this is uh,
Okay, okay, let's go ahead. Like, like it's okay.
so. If some function is derivable, we can actually something like you take differentiation and then integration, you get same function up to some constant. That is,
Okay, okay,
I think
okay. Like
if
I
that
thought, like maybe it have some other link to some other subjects and.
maybe I don't know. Uh, yeah, it is actually using some real analysis, nothing beyond that.
Okay.
Some because these functions now are over interval, and yeah, so this is just property of re- real
Derivative
functions.
and antiderivative, nothing deeper than that, mostly.
Yeah, nothing because of that. Okay, so in the second thing is that we can actually calculate what is its antiderivative. F is a continuous function with extra condition that the over closed curves integral of f is 0. Oh, then we can define its antiderivative by this function. So f of z1 by fixing a z0 inside omega, take any path from z0 to z1, any path, we can define over this gamma integral of this, and this is independent of given gamma. Why? So if there was a gamma prime, for example, from here to here, curve gamma prime, then gamma minus gamma prime, this is closed curve, starting from z0 and ending at z0, right? So integral will become 0, and we just use the property that initially I was discussing. They are also proved here, okay? Linearity and so on. So over gamma and gamma prime, these integrals are same. So this function is well defined. This is proved in the, if you have gone through the proofs, you know why they are well defined function, and that it is holomorphic also. It is proved using basic definition of holomorphicity. Okay, so the definition in the course, that definition we used and proved that f capital F is holomorphic, and that f prime is equal to f. Okay, so that's it. So the next question, next proposition is about that these two integrals, uh, either you take polygonal path or general curve from z0 to z or z0 to z1. Any path, either you take polygonal path or general curve. This this is let's say polygonal. Both these integral will be same. Okay. So now the, after this, let's see exercise problems, and we'll use them whenever needed, assuming that you know all of this from the class notes. Okay, so question number one. So in the whole assignment, this omega is non-empty open connected subset of C. Gamma is some curve. Gamma is given by e power I t, t belonging to 0 to 2 pi. We can draw the graph of this, right? What is this? This is unit circle, right? This is not well drawn, but you understand that, right? So the curve is starting at 0, going this way, and ending also. Sorry, curve is starting at 1 and ending at 1, right? Now we know the curve, and we want to calculate some value of integrals. So what is written inside this box? 1 by pi. Leave it like that. Whatever is written inside, we are taking. So the integral. So okay, we will calculate separately. So if we calculate this integral, then we will take real part and imaginary part. So that is what we need to calculate, nothing much more than that. Okay, so how do we start? So in this is sum of two functions, if you say, right? Z plus 1 by z. And what you know about z? Z is a polynomial, and polynomials are uh,
Holomorphic.
infinitely holomorphic. And so for holomorphic, if you have this function, this z, this identity function, it is holomorphic. And over any curve, what we have this, there is a definition of integral. Sorry, whatever. So we calculate this gamma just z dz. We want to calculate this box. Let's say this is given by s. S is equal to this plus gamma 1 by z dz, right? So we can calculate this integral easily. Do you know why? Because z is holomorphic and it has antiderivative. What is its antiderivative? Z square by 2. Z square by 2, if you take its derivative, it will become z, right? Now we just calculate with the endpoints. What is its endpoint? Uh, close first initial point is 1 and terminal point is also 1. Curve is starting at 1 and ending at fine. So this will become 1 by 2, 1 by 2, and it will become 0. So the next part will be this is 0 plus now we want to calculate this, and this is not holomorphic. And if you want to take its antiderivative in real numbers, if it was real numbers case, positive real numbers was our domain, then it would have been log of x. 1 by x has antiderivative log of x. In the domain 0 to infinity. But here in complex plane, uh, actually wherever this gamma is given, it's 1 by z has no antiderivative. Simply, I think some way logarithm is actually not well defined on complex plane. Okay, is that make sense? Yes, logarithm is not well defined. Okay, so that's known on whole complex plane. Once you remove one of the line passing through origin or one of the ray passing through origin, then it becomes well defined. So how we do this? So we change its, how do we do this? We apply change of variables simply. So what it will become in, so 0 to 2 pi. Now we are using the theorem which is proved in the class, some property of change of variables. So here we have to put in place of z e power I t, and this is f of z only. Right now this is just f of z. Into gamma prime we have to take. Uh, so what was that? F of z integral over gamma. This is same as uh, f of gamma t into gamma prime t dt. So AB here it is. So we are using this. So gamma prime t will be I into e power I t dt. Now e power I t from here and here it gets cancelled, and what we get is 2 pi I. Okay. So I hope you know this formula. So no need to write here. Okay. So overall, what we get s is equal to 2 pi I. Now, what is real part of s? 0. So now we want to calculate this. 1 upon pi, real part of s is just 0, plus imaginary part of s is 2 pi, you see from here, and now we calculate it. It's just 2. Okay. So I hope you understand z has antiderivative. 1 by z does not. Okay. So we use two different methods to calculate that. So the we have solved first part. You have any doubts, you can ask at any moment. Now see the second question. Gamma, sorry, right? Omega is a given non-empty connected subset of C. F1 and F2 be two primitives of F. Check the boxes corresponding to which statements, true statements are given. Do you know what primitive is? It's just definition I am missing right now. What it is? Primitive is just equal as other name of antiderivative. Okay. This is what is meant in this question. Primitive of F, primitive for F is antiderivative of F. I think so. Assuming that primitive is antiderivative, so we can see what is in the question. We are fixing a point W naught inside omega and defining capital F in this way. Over gamma, gamma is a rectifiable curve in gamma, omega. Initial point is W naught, terminal point is W. So in that case, F minus F1 is constant on omega. So in the class this week, if you have seen, this way defined function is well defined. Right now we discussed, and it's capital F prime of W or Z, whatever you write, is same as f of z for every z belonging to omega. Clear? This was first fundamental theorem, I think, just or second, a second fundamental theorem. But there was a little argument that when this function is defined, well defined, only if uh, the integral over closed curves is 0, right? Yeah, that is pretty obvious. It has already antiderivative. F has antiderivative. It's given. When f has antiderivative, integral of f depends only on uh, end points of gamma. Okay, so what is actually when you take gamma, a curve, integral of f dz, fz dz, what it becomes? Capital F1 of gamma of 0 or gamma of 1 minus capital F1 of gamma of 0, right? So this way we have. So when it is closed curve, it is already giving us 0. When it is closed, gamma is closed, then gamma 1 and gamma 0, these two are first initial point and end points are same. So this subtraction becomes 0. So this function is well defined. Capital F is well defined. Why? Since f already has antiderivative. F has an antiderivative and antiderivative. F capital F1 or F2 in fact is F1 small f and use a star. Let's say this is our condition. So it is well defined and this holds. Now the proof is obvious. How? You take f minus f1. This is what we need to calculate in the first part. Okay, this is a part. F minus f1 is a constant function on omega. So f minus f1 you take and its derivative will become f derivative minus f1 derivative. Uh, let's say evaluated at z, doesn't matter. But they are both same, fz and fz. So it becomes 0 for every z inside omega. And from here, what you calculate? There is only constant functions who have derivative 0. So this implies f minus f1. This function is constant function. Okay, so here we are emphasize here we are actually using the fact that omega is connected. So if we omega was something non-connected, opens up that, for example, two disks or a disk and a rectangle, whatever. So we can define a function here which is constantly equal to 1 and a function here which is constantly equal to 0 or whatever. So derivative is still 0, but overall function is not constant in this union of these two sets. Okay, so we are using that it is connected. So everywhere uh, function is same constant. Okay, so I hope it is clear to you. Now can you this this is constant, so this is true. What about second option? You can directly use part A, right? Is this true or false? I'm asking to you if you can also participate with me. F1 and F2 both are antiderivatives of F.
Yeah, it looks to be true.
So your guess is it is true, but my guess is it is not true. I will tell you how. Okay. See, one thing in the first part, we've shown that f and f1 both are antiderivatives of small f, and that they differ by a constant, right? So in f1 and f2 both are antiderivatives, no problem. But we only know that their difference is a constant. They might be equal, might not be equal. Okay. So, for example, you take these two functions, f1 be equal to, let's say, z, and f2 be equal to z plus 1. It is f1z and it is f2z. F2z of, then these both are antiderivative of what? 1. Wait, right? Because f1 prime is 1 and f2 prime is also 1, right? So they are antiderivatives of constant function 1, but f1 is not equal to f2. Okay. So this is an explanation for this. This is false. Now what about third option? f1 z naught is equal to 3, f2 z naught is equal to 1. If z belongs to omega, what can you say about difference f1 minus f2 of z? Is this equal to 2? See it once more, and some of you can explain, because there's nothing. I have already explained what f1 and f2 look like. Their difference is constant everywhere. Do you see here? F minus f1 is constant, where f was antiderivative of small f, f1 is also antiderivative of small f. Similarly, f1 minus f2, this is constant function. So f1 of z minus f2 of z, this is equal to c for every z inside omega, right?
Yeah, yeah.
So what we need it to calculate, what is the c, right? Because this is what is asked, c is equal to 2 or not. So how to calculate c? That is obvious, because f of z naught is given minus, sorry, f1 of z naught, f2 of z naught is also given. What they are given by c, because we are using this star condition for them
For
right
all
now.
these, C1 minus C2, which is like 2 minus 1, right? Like because Z and
Yeah,
whatever.
right. So this implies 3 minus 2, sorry, 3 minus 1. This was f of f2 of z naught is, f2 of z naught is what? 1. This implies c is equal to 2, and we are done. So their difference is given by 2. So the third option is correct. Is this fine? We can go to next question. Okay, so now we are in the third question. How to solve this integral means very easily. So which method you are to use? F is a polynomial and it has derivative, and it has antiderivative also. Fine. Are we going to use change of variable, or first write its antiderivative and just put the value initial point and terminal points? So whatever you want to calculate, you can calculate. I think change of variable will be difficult for here, because you have to put gamma t inside in place of z, and you have to calculate its cube and whatnot. So it will be good that we can calculate antiderivative, right?
Yeah, we, because it is holomorphic, we can use the first theorem, right?
First, yeah, right. So first part is, what is antiderivative of f? Easily we can calculate because it is polynomial. So we are going to write capital F of z is equal to, antiderivative of z will be z square by 2, right? Because we, when we derivative, we take derivative, z square by 2 becomes z, plus z cube by 2 factorial. What will be its derivative? Z power 4 by 4 into 2 factorial. Fine. Again, z power 4 by 4 into 3 factorial. Any mistake till now? No? You
No,
can point out any mistake. Right. So now we want to calculate what is initial point of gamma and terminal point of gamma. How we calculate? Initial point is given by gamma of 0. What is it? You put t is equal to 0 here. So gamma of 0 becomes, this becomes 0. This sine 0 becomes 0. So this is 0. Drawing, we can yes, we can draw the graph. But why to draw the graph? Graph is already, we see this, both functions are continuous and uh, infinitely differentiable. So gamma is a holomorphic curve, or gamma is a continuous curve, and it is defined on this compact set, so it is rectifiable also. So we just calculate initial point and terminal point. No need to draw the graph. Okay. Why to draw graph when we have initial point and terminal point? No. So gamma of 1, what it is? It will become 1 plus I, and then sine 100 pi, right? What is sine 100 pi? It's 0, right? So it is 1.
yeah,
So now we can calculate what is gamma of f, fz, sorry, integral of f over gamma, fz dz. This will become capital F of um, terminal point, which is 1, minus initial point, which is 0. Now so f of capital F of 0 will be 0, because there's no constant term in this polynomial. When we put z is equal to 0, it will become 0. Now we only need to calculate this part. So this part will be 1 by 2 plus 1 power 4 by 4 into 2 factorial plus 1 power 4 into, sorry, divided by 4 into 3 factorial. Now we can actually calculate this. uh, I don't know. So in the question we have been asked, this is in the multiplication. So let uh, multiply also. Okay, we cannot solve it. We can solve it actually very directly. Gamma of fz dz. We are multiplying by 4 factorial. So okay, 4 factorial into 1 by 2 plus 1 by or we can write 3 by 4 factorial plus 1 by 4 factorial. Now 4 factorial is multiplied everywhere. So what we are going to get? 4 factorial by 2 plus 3 plus 1. So 3 plus 1, 4. It is, I think, 16. What is, we can calculate it. 4 factorial is 24 and it is divided by 2. So it is 12 plus 3, 15 plus 1, 16. You understand the steps? Okay, so now that we are good that we can solve this kind of problems, but all that we need is when f is holomorphic and gamma is continuous curve or rectifiable curve or concatenation of rectifiable curves, then we can use these tricks. Change of variable when we don't have antiderivative. When we have antiderivative, we are going to use antiderivative method, just like this question. Okay, so coming to next question, we see here fz is given by z bar and it is not holomorphic, right? So antiderivative method is not working here. What some other method we are going to try? First, let this line segment is means we can draw this where it lies. We have complex plane and this line is from I to minus 1. I to minus 1. Okay, so we are able to draw the graph. We can also do the equation for the curve. Gamma of t is given by when t is equal to 0, we are getting I. So I plus when t is equal to 1, we are getting minus 1. Uh, so how do we write this? B plus I minus, right? So we can actually write the equation for the curve here. In this case, so 1 minus t is in 1 minus t here and t with minus 1. So when you see here, this is a linear equation, so it represents the line. And moreover, when t is equal to 0, we get this part 0 and this gives us I. When t is equal to 1, this part becomes 0, left part, and this gives us minus 1. Fine. So now we have this curve. So we can write in more uh, good this way. T I plus t minus 1 minus I. So whatever this t is belonging to 0 to 1. Now we have our line segment and we want to calculate modulus of the given integral. So let's calculate the integral first. We are using to change of variables. Change of variables. Gamma of f of z is integral of f of gamma t, gamma prime t dt. And because parameterizing interval is 0 1, so it is 0 1. So you directly write here gamma. So integral of z bar is, so always I'm making my verbal mistakes. So I hope I'm writing correct and you are understanding it correctly. So f of z, f of gamma t is becoming gamma t bar into gamma prime t integral dt 0 to 1. Now we put gamma t. What is gamma t? We directly put from there. Gamma prime t, gamma prime t is minus 1 minus I. Gamma t bar is becoming, we have to take in place of I, we have to replace it by minus I. So we directly write here 1 sorry t minus 1 into I. 1 minus t, I'm writing t minus 1 from here, so that we are taking conjugate, plus t minus 1, we can write minus t, so no need to complicate it further. Minus t we are going to write. So this is our given thing, and integral is from 0 to 1 dt. So minus 1 minus I, this is constant, so we can take it outside, and now inside thing is a holomorphic function, is differentiable function. It has antiderivative also, because in the, so right now in complex it doesn't, it is a conjugate function, but we can separate it out this way: 0 to 1 t minus 1, sorry, t minus 1, we can write a big bracket for this, t minus 1 I outside, because I is constant, dt plus, oh sorry, minus t dt 0 to 1.
Just one small doubt here. Since we already parameterized in a sense, why can't we go blindly and just see the result of this integration over the curve must be some sort of complex number, because we are adding and subtract, like in integration we are doing addition subtraction. We have already
Right,
parameterized, separated out the real and imaginary parts, and then we can
right.
uh, do you made a comment that internally it is holomorphic, like as one of the parts of the function. Do we really need to care about that, or like we can just go blind? I feel that we should be able to go blindly and
No, no. So this function does not have antiderivative when you take z bar, but when you replace it by t, that is what we are doing here. Now
yeah, t
our
belongs to real, right? T is in
right,
the
right.
real.
So after coming this place, you can blindly correct calculate.
Yeah. Hmm.
Yes, after this step you are saying correct, but before
Yeah.
this step, we need some careful observation. Okay.
Okay.
So
Okay.
from here you can directly calculate. I think you are correct, and we can directly put in place of t square by 2, and we can calculate. So, but I am solving it further. But anyway, we can leave this step and directly calculate here. What it will become: t square minus t I minus t square by 2, and what is outside? So minus 1 minus I, and here in this integral 0 to 1 we have to vary our t, right? Fine. So this is not needed, but we can write directly as you have pointed out. So what it will become: 0 when we put t is equal to 0, we get actually 0. So we just put it is equal to 1, and this part becomes 0. This becomes minus 1 by 2. So we have minus 1 minus I, and here into minus 1 by 2. So we get 1 plus I by 2. Fine. Now, what can we say about modulus of C, right? This is our question, modulus of this integral. We get this complex number. This is our C integral. Mod of C is equal to uh, what it is. This is 1 and this is 2. Sorry, 1 by 2 square plus 1 by 2 square, and we have to take square root. We get 2 by 4, right? Uh, so we get root 2 by 2, which is equal to 1 by root 2. So I think in your exercise problem, these solutions would be some integer so that you can write them. I hope there is no mistake, because we need an integer solution, but we are going, we are doing well. No? Any mistake, we can point it right now. So when t is equal to 0, yeah. So this curve is correct. Fine. We are using change of variable. So f of z is going uh, t minus 1 I minus t. Fine. Now gamma prime t, which becomes minus 1 minus I. Okay. Then minus 1 minus I we are taking outside, and we are directly calculating integral t square minus t I minus t square by 2. Fine. So the first integral becomes 0 because t square minus 2t is 0 at 1 also, and 0 at 0 also. So we only have minus 1 by 2 our solution. Minus 1 by 2 multiplied here, we get this, and fine. Right. So I hope this is correct. You also solving with me.
Yeah, like I don't think there's any mistake.
Okay, so assuming that this is correct, though I was surprising that we should get an integer solution, that exercises were planned to, so that we can give them integer solutions. For example, here you see we are multiplying by 4 factorial. Why? Just because making our integral an integer, so that submission of integer number is fine. Anyway, it is correct, and we are going to see next question. So the function is same, and C is also defined in similar fashion, but what? The curve is given by e power it. So let's draw the curve. We can draw at the same place. E power it is this circular curve. T is from pi by 2 to pi, means this is curve we are talking about, circular path. Okay. Okay. So again we have to calculate C and then modulus of this number. Okay. So what we are going to do, now that we have been given our curve gamma, we can directly use the change of variable. Gamma of z bar over gamma is equal to e power it, which is bar, is e power minus it, uh, from pi by 2 to pi into gamma prime, which is I into e power it dt. Now we can calculate after this is change of variable. So e power it get cancelled from numerator and denominator. We only get I. Taking I outside, we get integral t from pi by 2 to pi, and what it is, pi minus pi by 2 into I,
Just integral of I dt, like, yeah. Okay.
pi by 2 I. Now this is our c. So what will become 2c by pi? I, and when we take modulus of 2c by pi, it becomes 1. So we get an integer solution here in this case. Okay, you understand it, right? This is minus.
Yeah, yeah.
Okay, so we are going to see next question right now. Question number 6. F is holomorphic function on a given disk, Pz not R, and M is supremum of some complex number, some set of complex numbers, F prime Z, and given two element in the disk, we have to check which of the following is correct. The first part is A part. There exists W naught such that f of w1 minus f of w2 is equal to f prime of w naught w1 minus w2. So if you remember in real analysis, this is called
The
mean value
definition of
theorem. It is called mean
the,
value theorem, something.
uh, okay. But this looks
Lagrange,
something like definition of limit, right? Like if you take W1 minus W2 to the other side. Okay, this is mean value. Okay, okay, sorry.
there exists something in between. So what was that? Actually, when you have real line A to B, you have some interval, some function, let's say differentiable function. Then it is saying uh, the slope of the line is slope of the line is what? F of w1, so fb minus fa by b minus a. There exists some point where the slope matches. So this is the point, for example, here the slope of this tangent at this line, it is our w naught, for example. F prime at w naught is the slope of line joining uh, a comma fa and b comma fa. So but in the complex plane we don't have kind of intervals, but we have disks. So such that is there some w naught which at which derivative matches with this complex number. So
If if the function is holomorphic, then yeah, maybe we can apply all the theorems of real analysis to complex because individually, if you look at the components, real and complex parts, they should apply, and therefore, if it applies to the
mhm,
both of the real and complex, then it should also apply to the overall complex numbers. That is my intuition.
right, but I think we have seen, for example, if we take some function for which f prime is always equal, means some constant f prime is constant. For example, what will we have? F prime, let's say f prime of z is equal to 1. Then f prime of, so this f of z will be, let's say it is z. Now f of z is equal to z. Then okay, then this sum is not, this division is not well defined. So we have to take some other counter example. I'm thinking. So let's say f prime w is never 0. So this part is never 0 when, because w1 and w2 are different points. We're taking different points. Okay. So f prime z is equal to, so let's say non-zero always. This means we can take e power I z or e power z only, not y. E power z, this function. So f is also e power z. Fz is e power z. But if w is equal to 0, 2 pi I or 2n pi I, f of w becomes what? 1, right? So on the left side it is 0, because when you take and so on some numbers, if we take w1 w2 from this set, wi from this set, then left side is 0, fw1 minus fw2 is 0. But on the right side, f prime is always equal to some non-zero number, e power something, no? And w1 and w2 are so different. So there does not exist any w naught such that this right side becomes 0. Okay, so how to write this? We can write, if wi belongs to this set, then LHS of the equality is always 0, 0. But RHS is uh, never 0, never 0 when w1 not equal to w, and w1 is equal to w2, left hand side, right hand side both become 0. So that is not we are asking. We are asking w1 not equal to w, and we want something in the disk where they become equal. But nowhere in the disk w not exists such that RHS becomes 0. You understand this counter example?
See, but it is also sort of some there is some periodicity also, right, for this. So like can we define it over all wz, like as you are said 2n pi you are saying, but uh, like is the domain of definition of the function like going to like 3n pi 4n pi
Okay,
and
okay, okay. So it depends on the disk, for example. So one more thing I want to clear: f is holomorphic on the disk. So e power z, we are taking our function. It is holomorphic on any disk. Second thing is that the question is asking about general f. So we are giving a special f which fails. So this gives us counter example. And of course, we are not. We just take a small disk, for example, disk of 2 radius, something like this. One, some small disk, 2, 3, 0, sorry, 1, 2, I, 2I, 3I, something like this. some small disk where it fails, or just pi, 2 pi, 3 pi. In this small disk, we will get counter example. This counter example. No need to take whole complex plane. No need to take this big set 2n pi I. You can take some given set, given disk, whatever. You understand? Because that is also general given. No? D is given general disk. And if we want to give a counter example, right, we can change our disk accordingly. Fine, that you understand. So we can go to next question. Right, this question is long. We are going to solve part B now. What do you think about part B? I think it is correct because this condition is correct for real valued function, real function. So similar proof should be here. W1 and W2 both belongs to disk, and we get some, let's say, we get some curve from one point to other, some rectifiable continuous holomorphic curve we take, and if f is holomorphic, can we say what is its antiderivative? No. Is this proved in the class that if f is holomorphic function, its antiderivative exists? Not true in general, no? Or we have not seen any proof till now. Okay, so but if you right, but we are taking m to be supremum of modulus of f prime z's. Okay, so let's see what can we do for this. F fw1 minus fw2. So f prime, f is holomorphic, so is f prime holomorphic. I think it is not proved till now, but you will see that complex differentiable functions or complex analytic functions, they are infinitely differentiable. Okay, so assuming that they are infinitely differentiable, and first fundamental theorem, when we apply over this, let's say this is our gamma, this is part B, uh, dz, what we get because f prime, when f prime has antiderivative f, so f of gamma t, gamma prime t dt, and from w1 to w2, so we can write 0 to 1 because gamma is parameterized in this way, sorry, f prime here, and this value is also equal to f of w2 minus f of w1, because f prime has antiderivative f. So okay, one of the, if left side is equal to this. What about right side? Okay, so we take modulus of this fw2 minus fw1 is same as modulus of gamma f prime z dz modulus of this. And if you remember, there is an inequality of this integral of f prime. Do you remember this inequality? Integral over gamma of modulus of f. What this inequality is called, I don't remember, but initially it was proved in the last week maybe, or in the first when integral was defined first. Do you remember this inequality? Modulus of integral is less than equal to integral of modulus.
Yeah, yeah.
Okay, so and if you know that when curve is having antiderivative, then we can take any curve and it gives us same integral over any gamma. So we can take gamma to be line at any time. So this is equal to, now this is some constant on real number, some values z is varying, but we can take supremum of this. So we can take constant gamma supremum of f prime z, modulus of f prime z, z belonging to whole disk we can take, but we can take gamma only right now. Dz, fine. Now this supremum is taken over gamma. We can take supremum over whole d in fact. So this will, that will be more bigger. So integral over gamma supremum of z belonging to d prime, sorry, disk d of modulus of f prime z. And now you see this is a real constant, real constant dz. So we can take it outside because integrals are actually linear. So what we get here, uh, integral, sorry, supremum is existing here. Why? Oh, in the disk it doesn't exist, but in the gamma it exists. This supremum exists inside, means what, I don't know, but supremum belonging to real number, that is final, means it may not, there may not exist value where it attains it, this maximum is attained, but here maximum is attained just because gamma is a closed compact subset. Okay, so may not exist, but it is a real number, and this real number is given by m. So in the question it is given supremum of various f primes, what, it is given by m. So we can take m outside, what remains is gamma dz. And gamma we can take what,
Holomorphic. So we use
we can take any line also, or whatever, it will become w1 minus w2, that's all. Understand?
yeah, yeah, yeah.
Yeah.
That subtle point you made, right? Like the existence of that supremum. Can you please explain again? I could not catch it. I could not understand it very clearly. Like,
Okay. So when f is a function, continuous function from some domain to, so remark, maybe remark as a remark, what I was telling, when f is a continuous function from some omega, some set to real numbers, then supremum of uh, is supremum of fz, z belonging to k, exists is equal to f of z or f of w for some w belonging to k. From here, do you understand? When k is compact, when
Yeah, yeah.
k is compact. So this is what I was telling. Because gamma, the curve was compact, this supremum exists. Inside means some value will be. So this is what I was telling. There exists some w where it is attaining the value.
Yeah, yeah. In the same
Uh,
set.
right. When it is we are calculating in open set, we don't know it exists or not inside our collection, but it always exists because it is a bounded set. Oh, sorry. How it is bounded?
Because the soup is given as m,
M.
right?
Right. So we can assume it is already bounded and we can put it M. It is M. Right. So fine. We are almost done. Uh, what is this value? Length of gamma. And length of gamma here we can take line actually. Why I am taking line? So there are
No, this is just a Riemann sum, right? Like of the along complex numbers of dz. So it will be a straight. Like we don't need to care about the line. It is
so
independent of the
it
length.
will become M into W2 minus W1, right? But I was thinking we could have got modulus of W2 minus W1 because that these values are real and this B part is correct in that sense. So we are taking gamma to be line. So this is our gamma. And when you take modulus of this left side, right? Yeah, there was a little mistake in our steps. I don't know how I missed it, but fine. Uh, Here there are more steps to write. So when we explicitly take, let's say, gamma b line joining, line segment joining w1 and w2, then we can write its integral from 0 to 1 f prime gamma t gamma prime t dt, and then the next steps would have been this less than or equal to uh, integral from 0 to 1 gamma f prime gamma, sorry, f prime gamma t here in modulus gamma prime t. This is also in modulus dt. Now we take supremum of these numbers and this is equal to this is less than or equal to m. So we delete this step and what is left inside is m. So this is less than or equal to, we can just copy it from here and put it here. Okay, so this is less than or equal to 0 to 1 gamma prime t dt in modulus, and this gives us a length of line joining w1 and w2, which is w1, this is equal to m w1 minus w2 or w2 minus w1 mod. Is this fine now? I think we got the option correct. So once more, let me recall this. So the integral along any curve would have been calculated. Okay, because f prime has antiderivative, which is f. So when we calculated f prime z using antiderivative method, we got this integral equal to this. Now what we are doing is taking modulus of this integral. So we get modulus of f of w2 minus f of w1 is equal to modulus of the integral, and we are taking gamma line joining w1 and w2. Now after this, what we did, we just use change of variables here. Then in the next step, we use this inequality, uh, which I don't know what is inequality called by the name, but this inequality, this step is crucial. And further, this f prime of various numbers, of f prime of various gamma prime, gamma t belongs to the disk. So okay, no problem. Okay, so assuming that we did this somehow, we still have more time, so we'll solve more questions. Now part B is done, it is correct. How about part C? So the above inequality is strict inequality. F is general function, this is also a general thing. Is this strict? So in the above inequality, where could have where we could have found this strict inequality? So the only option is here, right? So but it is not always true. For example, when f prime is some constant, it is constant everywhere. So supremum is the same number, right? So this supremum of the same numbers is same number. For example, I was talking about f prime z is equal to some constant 1, let's say for example fz is equal to 1. That will give us a counter example. Let me write it. This is about part C. When fz f prime z is a constant, let's say equal to 1, then m is equal to 1. And what uh, and this is always equal. There is no strict inequality. And then fw1 minus fw2, this modulus is always equal to modulus of w1 minus w2. So we not necessary we how to write this. So it is not necessary that strictly. So the above inequality is not necessary, not necessarily uh, strict. Fine. You understand this counter example? Okay. So let's see. This is wrong. Stick is not correct. The function f is uniformly continuous on disk tz0 r. So what is uniformly continuous definition? Part D, f from omega to, sorry, real number of complex number or any topological space is uniformly continuous when if given any epsilon positive, there exists delta positive depending on only epsilon, such that f z1 minus f z2 is modulus is less than epsilon whenever z1 and z2 are delta close. Z1 minus is less than delta. Yeah. You understand the definition here? Some author I think write this way: 0 less than this modulus less than delta. But that is for limits. But both are equivalent in our case, so we don't care about this because it is continuous. At 0 we get function value only. So after this definition, we have to check when is f uniformly continuous or not. And if you see part B implies what part B implies, part B implies f z1 minus f z2, this modulus is less than m modulus of z1 minus z2. What less than or equal to, sorry, less than or equal to is needed because part C implies equality. Inequality is not strict. Okay, so what this implies? If you give me an epsilon, let's say given any epsilon positive, what delta you are going to choose? Let delta be equal to epsilon by m. Then what happens? Z1 minus Z2 less than delta implies uh, modulus of fz1 minus fz2. This is less than or equal to m, and this is less m delta because z1 minus z2 is modulus is less than delta, but m delta is equal to epsilon. This implies that f is uniformly continuous. So any condition which is like this on a given domain, this implies f is uniformly continuous. Okay. So from here you see any linear function, real valued linear function, because they have this m to be constant, they are means if fx is equal to mx or plus c or minus c, whatever you want to take, these are uniformly continuous function on real line. These are uniformly continuous on R because they satisfy this condition. Okay, so one thing I was again mentioned that in the definition of continuity, what we take, we say that f is continuous at a given point, but In the uniformly continuous definition, we don't fix any point, but so there also given any epsilon, there exists a delta which depends on epsilon and the given point. Here, delta is depending only on epsilon, not any given point, and it works whenever 2 points are delta close, their images are epsilon close. Okay, so coming to next question. Z0 to Z1 we have a line segment. Then modulus of integral of 1 by z square dz is less than or equal to 2. Okay, so let's draw the graph because this is line segment and we can draw this. Line is joining from 1 minus 1, 1. This point is here and the point is here. So this is our path starting from here, ending here. So let's say we calculate the integral. Okay, so let's start calculating what is modulus of 1 by z square uh, gamma dz. It has antiderivative. Do you remember what it is? Uh, minus 1 by z. Why we are taking antiderivative? Because f is holomorphic. Where f is holomorphic? C minus 0. And we can take what domain? Some domain here, some open set here, which does not belongs to. Let's say this is our omega. So let omega be uh, x plus iy such that y is positive, or this is also given by upper hyperplane. There 1 by z square is holomorphic. In H, 1 by z square is holomorphic and has antiderivative. Antiderivative. So we can use antiderivative method and we calculate this W1 W2 here. So we get 1 by W1 minus 1 by W2, and we have to calculate modulus of this. So we take modulus of that. This is just explanation, so you can write it as rough work. Okay, so what is this modulus is equal to? What is W1? 1 by, we are actually calculating what is in integral, and we will say that modulus is less than 2. 1 plus I minus 1 plus I. This modulus, this is equal to minus 1 plus I minus 1 minus I divided by 1 plus I into minus 1 plus I. So in the numerator, we are going to get minus 2 divided by 1 plus I, 1 minus I. What becomes? Minus 2. Is this fine? Because in the denominator, it is becoming I square minus 1. Let me write one more step here. I square minus 1, which becomes minus 2 divided by minus 2, hence it's equal to 1. So we are taking modulus always, so That's it. So you understood this problem, right? We calculated integral, and in calculating integral was easy. Why? Because we choose our domain specifically where f is holomorphic and it has antiderivative also, so no problem. So this option is correct. Less than or equal to 2. We are getting 1. That is fine. Do you see any mistake or any doubt? Okay, so now that you understand this, we can go to next question, which is about uh, again the gamma is same. So this is always incorrect because option A is correct. Both things cannot be happening together. Why? Law of trichotomy. When A is correct, B is incorrect. What about last option? Gamma t is given 2 e power I t 0 to 2 pi, sorry, pi by 2. Integral is less than 6 pi by 7. Okay, we are going to draw the picture because this in the part C we have clear picture where the what is the curve. This is 1, this is 2, and this is a curve, the 1/4 of the circle. This is 2 e power I t. Starting from here, ending at here, because starting from 0 to pi by 2. Now we have this gamma. We want to calculate the integral. Let's calculate this. Function is z plus 4 divided by z cube minus 1. Z plus 4 z cube minus 1. Right. Integral over dz. So okay, how to do this? This function is okay. Where is inequal? The function is having problem in this circle. At here, at somewhere here, and somewhere here. We don't know actually. So where roots of entry?
At all
The
the cube roots of one, it'll not be holomorphic.
right. So but we can choose our domain accordingly this way. This is our omega where this function is holomorphic, right? And when it is holomorphic, we, right now we don't know what is its antiderivative, but we can try to calculate. But okay, one more thing. Um, we want to calculate modulus of this, right? So modulus of this is less than modulus of we can break into two gamma z I z cube minus 1 modulus dz plus 4 by z cube minus 1 dz modulus. Or sorry, we can what we can do is somehow we have to bound it by some number, right? So not doing this way, we can use change of variable and get our equation like this. Using change of variable, we get uh, 0 to pi by 2, 2 into e power it plus 4 divided by e power 3 it minus 1 dt. Now, when you take modulus of numerator, modulus of numerator, it is bounded by 6. Triangle inequality using triangle. You understand this? So what we get when you take modulus of this, let me not copy, we have to write it. Modulus of integral of z plus 4 by z cube minus 1 dz. This is less than or equal to 6 in coming from numerator, integral 1 by z cube minus 1, this modulus dz. No, not, we are now taking all the reals, so we can use the change of variables. Right, sorry, 2 into what we have to write here. In place of z, we are writing 2 e power it. So 2 cube 3 it minus 1 is modulus dt 0 to pi by 2. Fine. So 6 is coming from numerator because numerator is bounded by 6. What I'm using? Triangle inequality. Triangle inequality says z1 plus z2. This modulus is less than or equal to mod z1 plus mod z2. Fine. Right. Now we are thinking about denominator, what it could be. When you take so and another inequality we call reverse triangle inequality is that z1 minus z2, this mod is greater than or equal to modulus of z1 minus
Minus
modulus
Z2.
of correct. So here if we put z1 is equal to 2 e power it, so what we get here is that 2 e power 2 cube e power 3 it minus 1, this is bigger than or equal to this modulus z1 becomes 8 minus z2 becomes 1 only, which is equal to 7. So when you take 1 by means take the inverse of these real numbers, 2e 2 cube e power 3 it minus 1, this modulus is less than equal to 1 by 7, right? So there was one more missing thing. When you take change of variable, you write extra thing here in this place, gamma prime t. So there are mistakes. We are not calculating. Gamma prime t is what? 2i into e power it. Okay. So the same thing will come here, 2i into e power it, because when you are taking modulus, it just become 2. So here we will get 2. Right. So solving it further, we have to bound it by 6 pi by 7. Right. Anyway, 2 into, so everything is bounded by this 2 by this is bounded by 2 by 7. So what we get here is this. This is less than 6 into 2 by 7 into integral of dt 0 to pi by 2. Now it is correct. This integral can be calculated. 12 by 7 integral is pi by 2, and this, solving it, we will get 6 pi by 7. So these are rough works. We should mention them. Right. Do you understand where you don't understand? You tell.
We have to use the inequalities cleverly, right?
Right.
Yeah. I don't think this. I tried doing by brute force, but I could not find the exact number. I come to the exact number. Maybe, it comes into the tan inverse and all those things I was trying. So
Okay. Good that you're trying, and I hope now after looking at this, you understand the, the easiest way to do this
yeah,
because
it's like after many, but this is a very neat way of doing it. Like very clean and very nice.
yeah. Okay, so we are almost